Welcome back. In the last video we saw how to tune one of our machine learning models, specifically the k-nearest neighbors classifier, by hand. Now this is hyperparameter tuning. What I've done is I've just adjusted this little title here to say hyperparameter tuning by hand. But as you could imagine, if you had more than one parameter or hyperparameter, in our case we only tuned n neighbors. We go up to the k-neighbors classifier. We only tuned this one parameter. If we wanted to tune all of these, they could get a bit tedious. We'd be writing for loops for days. So what we're going to do here is, and remember we've also written off our k-nearest neighbors, we're in the search of better results. So because our logistic regression and random forest classifier are performing better, we're going to cut the k-nearest neighbors model out of our experimentation. So now we're going to go hyperparameter tuning with randomized search CV. And so this is what we saw in the scikit-learn section. And if we search it up, randomized search CV sklearn, we'd find it here. Beautiful. So there's the documentation there. You can read through that on your own time, but we're going to see it implemented. And again, if you're wondering how you could find the hyperparameters to tune a certain machine learning model, well, here's what I would do for logistic regression. So how to tune a logistic regression machine learning model in Python. Something like that. If we search that up, logistic regression model tuning with scikit-learn, beautiful. Logistic regression using Python, scikit-learn, hyperparameter optimization of machine learning models, tuning parameters for logistic regression. If we were to go through these and research it, do our own experiments and figure out things and ask more questions, you'd probably find some pretty good answers. But for now, we're going to pretend we've gone through those steps and we've figured out that we can use randomized search CV and that we can tune a bunch of different parameters. Let's do that. We're going to tune logistic regression, our logistic regression model, which is that, and random forest classifier using randomized search CV. And again, if you need information about which parameters you can use for logistic regression, I've even spelled that wrong. Typical Daniel. Logistic regression and random forest classifier, you can go up here, sklearn logistic regression. So if we look in here, this is going to give us a list of different parameters, and you might read the documentation. And trust me, I did this. The first time I did this, I read the documentation and I'm like, this means all of these terms like elastic net, L2 penalties, bool. Actually, I know what bool means. True or false, right? All these things didn't mean much to me. It was only once I started to do some research and go through and figure out what all these different parameters actually meant was that I started to understand it. And the same goes for the random forest classifier. You could do the same thing. Put that into the sklearn documentation, or change this to be how to tune a random forest machine learning model in Python. These are steps that people like machine learning engineers and data scientists take every single day to figure out how to improve their models. No one in the beginning knows how to do this off by heart. Even after doing it many times, I still have to look these things up. So we go here. Let's see how we would do it. So the first thing to do with randomized search CV is, and if you're wondering what CV stands for, it stands for cross-validation. We saw that in scikit-learn. And more specifically, cross-validation, what it does is instead of doing a normal train and test split like we've done before by creating one training split and a test split, aka 80% in the training split and 20% in the test split, it creates, this should really be K, but I've done 5 because it looks nice here. This can be K-fold cross-validation. So 5 is the default in scikit-learn in the latest version, but you can really adjust this. And what it's going to do is it's going to create 5 different versions of training data and 5 different versions of the test data, and then evaluate different parameters. Remember, because we're doing hyperparameter search, evaluate different hyperparameters on all of these different sets of all of these versions of the training and test data, and work out which set of parameters or hyperparameters is best across these 5 different splits, rather than just being one single split. So if we go here, let's do it. So what we need to do is create a hyperparameter grid for logistic regression, and reading the logistic regression documentation as well as searching up here for logistic regression, we figure out that there's a few hyperparameters that we can tune, such as the value for C, which if we look in here, if we go down here, C, so inverse of regularization strength must be a positive float. Like again, you could read this the first time the documentation and go, what do any of these words mean? That's why it requires research to check it out. And then there's another one called solver. So we'll go here. We'll just have a look at what a parameter grid looks like. C, and again, there are more. We're only using 2 here. So we're only using C and solver. You might find in your research that you could adjust the penalty, you could adjust the fit intercept, you could adjust a whole bunch of hyperparameters, but the overall concept of adjusting hyperparameters is what we're focused on. So we're going to set this. After our research, we know that a good value is NP log space, -4. And if you're wondering what the log space, because I'm kind of throwing these things out relatively quickly, log space does, if we go here, returns numbers spaced evenly along a log scale. So the start, stop, number. So this is going to be between -4, between 4 and 50 of them. And if you're wondering what a log space is, these are the ways you can do it. Let's go, what is a log space? Log space reduction, L complexity. Can you explain in simple words what is log space reduction? So we could read that. Again, fair few complex words there, but after a little bit of effort, you'll be able to figure it out. So we go here. We're going to only really use one solver here because really after the research and finding what hyperparameters we should adjust, we find that C is probably the most valuable one for logistic regression. So we're only going to use one value for solver. So really what we're testing here, we're creating a grid of numbers on a log space between -4 and 4. So there we go. Oh, sorry, because it's a log space, it's 1 times 10 to the power of -4 up to 1 times 10 to the power of 4. So a pretty big space there. These numbers are pretty well separated. So let's get rid of that. And now we'll create hyperparameter grid for random forest classifier. Wonderful. And through our research, we find that some of the best parameters for a random forest are number of estimators, which is, if we're using a random forest, and estimators is how many trees that we have in our forest. So NP a range. And you might be wondering why I'm using ranges here when I'm going through this. Well, the reason is because if we look up the documentation, I know in a previous video we haven't explicitly used range, we've used a list. Just for a refresher on what a range does, let's check out this. So it's basically just going to create a range of numbers, space 50 apart, because of 50 here, between 10 and 1000. So if we look up randomized, I think we already have it. Maybe here, there we go. There's somewhere here. In contrast, we go, it is highly recommended to use continuous distributions for continuous parameters. So that's why we create a range of different values. This is where we read that from. Rather than just being an explicit list, we're creating a range of continuous distribution for our hyperparameters for randomized search CV. But that's just in the documentation. So we go here, you could still just use a list. But the documentation of people who have written the sklearn library recommend us to use a range of values. So we're going to go max depth here, which is another one that we found through our own research of a hyperparameter that we can tune. Remember, for any machine learning model, a quick search of going, hey, I'm using this model, I've figured it out, I followed the scikit-learn, I don't have the map, do I? Yeah, we do. I followed the map and I've decided I'm going to use a random forest classifier. How can I do hyperparameter tuning of it? Well, that's where it comes to searching something like this, right? So we'll go here, we find that another one is the min samples split. And then we go here, and we'll use a range actually. I've said that we're going to use a distribution, but here, max depth, we haven't used a distribution, we've just used an explicit list. But we'll use another range here. And then we'll go here and we'll also use min samples leaf np arrange 122. Beautiful. So now we have two hyperparameter grids for the two models that we're going to try and hyperparameter tune using randomized search CV. So what we'll probably do is we'll end this video here and then we'll come back and we'll use these two grids along with randomized search CV to try and improve our results of our logistic regression model and our random forest classifier beyond what we initially got. So beyond these initial values that we got. And remember, these values were obtained without using cross-validation because we only used a single train and test split. Whereas, if we go into Keynote, in cross-validation, so this is what we used to get our original scores, a single train and test split, whereas in cross-validation, we're going to be using multiple train and test split. Remember in the scikit-learn section, we discussed that if you're going to provide a metric in terms of how a model is performing, it's probably best to use a cross-validation metric, especially with classification problems. So let's revisit that in the next video of tuning our random forest and logistic regression with randomized search CV.